Lab 2, Motion of a Falling Object. The main purpose is to apply Newton's laws of motion to the real world. The experiment today involves the motion of an object in one direction with a net force, and using Newton's second law of motion, if there is a net force, then the velocity will be changing. We'll see just how well this fundamental principle predicts the dropping of a crumpled paper ball from rest. We have our paper ball video loaded into the tracker. The ball's motion is analyzed from v equals 0 to before the ball hits the ground. As we can see, the origin is at the bottom of the ball and it's moving in the negative y direction. This data is then used to compare to the computational model. Our first computational model will be with gravity, and we make a few assumptions. For one, there's no drag force, so we just assume that the net force is simply the force of gravity. Now, to create a computational model, we first initialize the mass, and then we initialize both the position and velocity to 0. We start our time to 0, and then we take this delta t of 0.001, which is smaller than the frame rate of the video, to allow a better iterative approach. We initialize our gravity force, or gravity acceleration due to gravity, 9.8, and then this j hat vector allows us to vectorize all our magnitudes to the y-axis, which we're working with. Then we create this loop where t iterates up to 0.3 seconds, which is the time of our observed model. Then we create this net force. Our net force here is simply the weight, and to calculate the weight, we use this force equals to negative mass times g, which is the acceleration due to gravity. And we plug that in, and we multiply it by the j hat value, which vectorizes it to the y direction. Then we can simply update the velocity using the velocity update formula and the position using the position update formula. Then we advance the clock. As you can see, this computational model draws parallels to our observed model, and then we are able to also make another model where we include both the gravity and drag. So the two forces acting here, we're assuming, are just the gravity force and the drag force. So everything remains the same to just the gravity model, except we add this proportionally constant that we initialize. Then everything remains similar here, except we do have to include the drag force in this F-net calculation. The weight remains the same. The F-net calculation, we use this formula to calculate the drag force, proportionality constant times velocity squared. Plug that in, we multiply it by j hat again to vectorize it to the y direction, and the other components remain the same. And as you can see, this is pretty similar to the original model by first glance, but we then take the data from both of these models and load it into a graph. Now we have the position versus time graph of our models versus experimental data. We can first see with the gravity model in black that it does dip below slightly from the other two models. This aligns with our assumption that drag force does not exist, and we can see it does exist with the experimental model right above. We can also see with the experimental model in blue and the gravity and drag model in red that at 0.25 seconds they do have their slope flatten out. This highlights the idea of them reaching terminal velocity, where the gravity force and the drag force equal each other, thus the net force is equal to 0 and the velocity is constant. We can also see a discrepancy between the gravity and drag model and the experimental model. This can be highlighted for two reasons. One, the shorter time frame could have caused issues in tracker, as one issue in this short time frame could have been magnified greatly. Additionally, an additional wind force could be present with such a light object like a paper ball, and add an additional force to our gravity and drag forces, which we only accounted for. This could be improved with the longer time frame, and also either having a heavier object instead of a paper ball, or having a more controlled environment. Now, what does it mean? In regards to terminal velocity, the gravity and drag model more closely aligns, as at 0.25 seconds the slope flattens out, in comparison to the black gravity model where the slope is constantly changing all the way through. Terminal velocity itself is when the drag force and the gravitational force equal each other, and since these are in opposite directions, when calculating the net force, it'll be equal to 0. Additionally, if the velocity is constant, this must mean that the net force has to be 0 to create the consistent velocity. Now, what if the object were initially thrown downward? What would happen to the terminal velocity? We know when terminal velocity is reached, the net force might be equal to 0. Since the gravitational force would be constant, the only thing that can change is the drag force. This means that the terminal velocity should remain the same. So we can see in this graph, without initial velocity, it reaches terminal velocity at about negative 4.7 meters per second, and we can see with this initial velocity added of negative 3 meters per second, it reaches terminal velocity at the same negative 4.7 meters per second.